My name is Louis Baumier. I'm with the Institut de l'Énergie Trottier at Polytechnique Montréal. On my name and on behalf of Natural Resources Canada, I want to welcome you to this first of 5 sessions of modeling project presentation. A few housekeeping rules. Like I said, it's a busy agenda. We will limit all the presentations to 30 minutes, including Q&A period. Please keep your microphone on mute. You can post a question in the chat box if you don't want to ask it during the Q&A period. Raise your hand when you want to ask a question. And also, this session is being recorded and will be made available online after in the hours or days following this first presentation, this session. Very few words about this initiative. It's I don't want to take too much time. Like I said, I want to leave all the time for people that will be presenting. So if you want to know a bit more about this initiative and what we've done in the past year and a half, please go to that email address, this website, and consult all of the reports that we have been producing so far. So today we'll have 4 projects that will be presented. Those are projects that have been funded by this initiative this year. And I would like to start right now by asking Madeleine McPherson from University of Victoria to give us the presentation about her project. So Madeleine, now the control is yours.
Great, thank you, Louis. I'm just going to share my slides here. Okay, can everyone see those okay?
Yes.
Great. Great. Well, thanks so much, everyone, for taking the time to join the session today. My name is Madeleine McPherson, and I am an executive member of the Energy Modeling Initiative, as well as an assistant professor at the University of Victoria. And here with me on the line this morning presenting is Rick Hendricks, who is a PhD student at the University of Toronto. And we're really delighted to be kicking off the EMI webinar series with an overview of the database project that our team has been putting together over the last couple of years, really. Rick and I are presenting on a much larger team who have been absolutely instrumental in pulling this project together, including Jacob Duraz, Tristan Kusi, Dustin Aldana, Jacob Monroe, and Yuha Kibiluoma. So together we form part of the Sustainable Energy Systems Integration and Transitions Group, or SESIT, at the University of Victoria. And specifically, we're housed within the Institute of Integrated Energy Systems, or ISVIC, at the University of Victoria. This presentation is really the first part of a 3-part series, which we will be with the next 2 webinars in today's EMI series. And together, these 3 projects or webinars are really distinct pillars within a larger, more cohesive modeling workflow. Each of these 3 work packages together are contributing to the broader research question: how can we model the electrification and integration of our energy systems to explore and implement deep decarbonization pathways? And we believe there's really 3 pieces of software capacity that are needed to work together in tandem to operationalize the development and use of modeling work in the decision and policy-making process. So this first presentation from Rick and myself is really focused on Pillar A, the data inputs to our modeling workflow. The next sessions this morning will come from Mo and Mohammed, who are going to take us through Pillar B, which is really about visualizing the outputs from modeling work. And finally, the third session this morning will come from Robert, Maddie, and Lauren, who are going to be presenting on an integrated modeling framework that they've developed, which is really part of Pillar C. And all of this is, again, part of this much broader workflow, working its way all the way up to supporting decision makers. So in today's presentation, Rick and I are going to start us off with a review of Coders, which is a large database that we've been assembling to really populate our sector-specific models that sit within our broader modeling suite. In today's presentation, I've touched on our overarching objective, and now we're going to move on to some of the data challenges that we've faced and how several key priorities have informed our database design decisions. Next, Rick is going to walk us through the Coders database itself and how this links up with our SESIT modeling suite, specifically as it pertains to some of the electrification and integration questions that we have. And then finally, I'm going to wrap up with some closing remarks on limitations that still stand and what our future work might look like. So the challenge that we face from a data perspective and more broadly, we feel within Canada, really comes down to barriers between modelers and decision makers. And this barrier really impeding some of the deep decarbonization efforts that we need to operationalize if we're going to hit some of our climate mitigation targets. In particular, the information flow across institutional and disciplinary boundaries has been slow and opaque. And overcoming this really requires new approaches to navigating the modeling decision maker interface. And key among these, the ones that we're really going to focus on today, are the models and the data inputs themselves, which have historically been unavailable or lack transparency. In particular, when we compare Canada's landscape to the United States and Europe, what we have is something that's disjointed and somewhat ineffective. So in the US, there's a multitude of sources of electricity system data. One of the big ones that we look to a lot is from the Energy Information Administration, which I'm sure many of us on the line are familiar with. And in Europe, there's sort of a similar institution, ENSO, which collects and distributes real-time supply and demand for all of its member countries. In Canada, on the other hand, our electricity system data is often published at the provincial level. And the suite of data is that each province publishes varies, both in terms of the content that's published, as well as the spatial and temporal granularity of that data and the formatting of that data. And this inconsistency makes it really difficult to collect and use the data in our modeling, in our models. So the results of this landscape, this data landscape in Canada, are substantial data gaps that leave modelers with inadequate resources to perform in-depth and timely analyses of Canada's low-carbon energy transition, which in turn frustrates the efforts of policymakers while depriving the public of complete information. And when we try to dig into this challenge a little bit deeper, what we see is that there's really three critical but lacking components to the integration of model-based evidence into the decision-making process. And we boil these down into timeliness, transparency, and inclusiveness. So the challenge of when, timeliness. Data collection is often a hugely time-consuming step in the modeling process. So just to give you a little bit of context for what we mean there, the SESIT team has spent almost 2 years now collecting data pertaining to Canada's electricity system. This is data that includes generation assets, transmission network, and load data, which Rick is going to speak to in a minute here. This timeline is really non-workable from a decision maker's perspective, who often have defined and limited windows to propose policy or implement programs. So our solution to this is to assemble the data needed for each of our models in what we're considering sort of this standing database that we're planning on continuously updating and making available to others. Our hope by doing this is to overcome one of the most time-consuming and frankly frustrating aspects of the energy modeling process. The next challenge comes down to the what and transparency. I'm sure many of us have heard the trope, garbage in equals garbage out, in part because it's so true. When we're presenting our modeling results, many decision makers and stakeholders in the room often very rightly ask, but what were your model inputs? The problem is that energy systems models leverage thousands of data inputs, which can be really difficult to communicate to stakeholders and decision makers. By creating a proper database, we're hoping that we can make a significant step forward in terms of injecting some transparency into the modeling workflow. What do we mean by proper? We mean open, shared, version controlled, and standardized. And then finally, the question of how, inclusiveness. To carry the weight required to impact decision-making, the modeling process itself has to convene a diverse range of disciplines, perspectives, and stakeholders, specifically in the scenario definition and data definition stages. So inclusiveness here, we're including a broad range of stakeholders, so making model inputs and outputs accessible in a user-friendly format, as well as a range of modeling teams who are able to interact with, use, and potentially even contribute to the database itself. So coming back to our primary question, how can we model the electrification and integration of energy systems to explore and implement deep decarbonization pathways? What we're trying to argue here is that we need a new platform that delivers a holistic understanding of electrification, energy systems integration, in order to get at those deep decarbonization pathways that inherently will be integrated. But one that also sits within an institutional structure that is conducive to and effective in the decision-making process. Such a platform needs to integrate insights across spatial temporal scales and explore opportunities for flexibility and efficiency gains at the intersection of systems and vectors. But it has to do so in a way that is still computationally practical and policy relevant. Looking through this list, what we see is that we need to assemble an integrated suite of modeling platforms that are then supported by an integrated and consistent set of data. So the CESIP modeling suite is attempting to pull together this integrated and holistic perspective by representing each of the systems with each of the energy systems by a standalone model. Making this decision allows us to address the full complement of sector-specific operational constraints. It allows us to leverage a diverse and appropriate suite of modeling methodologies within each of these sectors. And it also allows for a lot of extensibility. We can swap alternative models in and out of the platform. We can use certain models or not use certain models depending on the research question, so on and so forth. But looking at this suite, what you can see also is that this is going to require an extensive amount of data to populate each of these models. So at this moment, I'm going to pass it back over to Rick, who's going to talk about each of the data inputs to these models and the coder database specifically. So over to you, Rick.
Thanks, Madeline. Good morning, everyone, or I guess good afternoon for those a little further east. My name is Rick Hendricks. I am a PhD student in civil engineering at the University of Toronto. And I have been, I guess, the primary person responsible for gathering all of this data over the past 18 months or so. And we're sweltering in the sunshine here in Southern Ontario today, so I'll try to shed a little bit of that light onto the coders database. Just as a start, I'm going to use a legend throughout these slides, and I'll just explain what the legend means. So the dark green indicates data that we've obtained, so high quality data that we've obtained from a variety of sources. Some of them are utilities, system operators, government, etc. The pale green indicates data that was not available, or at least not available in the format that we would have preferred. And so we've had to calculate, measure, or estimate the data to acceptable thresholds of error. And some of the data is still under development, meaning that we have a request that's outstanding to a data provider, or we're still in the process of sorting through the data. And the red is data that we still need. We weren't able to access it, and we don't have it from measurement or calculation. Next slide, please, Madeline. So the first model in the suite is a capacity expansion model. And the model being used by our group is called the Canadian Opportunities for Planning and Production of Electricity Resources, otherwise known as COPPER. And it's a capacity expansion model, as I mentioned, and it assesses how the electricity system might evolve in terms of generation, transmission, and storage in response to evolving needs. And also how that evolution is affected by changes. It could be changes in demand, changes in technology, policies, etc. And it's a Canada-wide model, although it could be used at the provincial level or maybe a regional level with multiple provinces. And we're considering some of those options to use it beyond nationally. And it's also a static and dynamic model. Next slide, please, Madeline. So this model requires a fairly broad suite of data. I won't obviously get into each of these data points. But to give you a high level sense, we need load data, transmission data, generation, policy, what are the carbon policies, what are the other environmental policies or energy policies that are in place that we want to model, and some other data, particularly around natural gas. So this tends to be fairly detailed data. At the transmission level, just to give you some example, that was probably the most difficult data for us to obtain because we're trying to get length data, voltage, reactance, not so much for this model, but for other models. And so it's been quite a challenge. And the hourly data has also been very important for our models, and that's been challenging as well. Next slide, please, Madeline. So on to that next model, which is the electricity dispatch model. And it's really the cornerstone of the modeling platform. And the model that we're using is called the Strategic Integration of Large Capacity Variable Energy Resources, which is a bit of a mouthful. So we just call it SILVER for short. Copper and silver, creative names, very clever names. Basically this economic dispatch model takes the outputs of the capacity expansion model and assesses the operations. So it looks at the operational level. If the capacity expansion model says, this is what we should build from a lowest cost perspective, the dispatch model is saying, well, can you actually do that? What does that look like? And what are some additional costs, or cost changes that might occur at the operational level? Okay, next slide, please, Madeline. In terms of data, of course, since this is an operational model, looking at the operational level of the system, we need much more detailed data at the hourly level and at the operational level of the various assets within the system. So generally, we have more data gaps in coders in the database in relation to the dispatch model than the capacity expansion model. But we are working through these. As you can see, several of these are under development. And we have a few more sort of red areas here where we're data that we're still seeking, particularly in Saskatchewan and Manitoba, around transmission, design, and operations, as well as hourly load within the provinces and between those provinces. Next slide, please. So the third model is a transport sector model. And a transport sector model is important because incorporating this kind of a model into the platform enables analysis of transport electrification, which will be a key issue going forward, through both electric vehicles as well as hydrogen vehicles. And it's also a multi-layered model, and my colleagues will be speaking about this model in a future presentation later today, so I'll leave the details to them. For our purposes here, it includes several energy vectors, modes, and node types. So all of these, as you might imagine, tend towards data requirements. Next slide, please. So the focus of this model has been within the city of Regina. So this table relates only to that, the status of data for that modeling purpose. And in general, we've been quite successful at getting the data in terms of modeling transportation within the city of Regina. Either we've obtained the data or we've been able to calculate the data. There are a few things that are still in the works, but overall we have what we need to implement the transport model. Next slide, please. And of course, there's a building model, and incorporating a multi-vector building model enables exploration, as you might expect, of things like heating electrification, on-site behind-the-meter electricity generation, and demand response, all of which are key aspects of electrification and decarbonization. So the models we are using are largely existing models, but we're leveraging and adjusting those models for our purposes. And again, my colleagues will speak to that in more detail. Next slide, please. So in terms of data availability for the building system model, we characterize it in terms of availability at the building specific level, at the building archetype level, and then also we're gathering data from surveys about various aspects of the built environment. And the data collection here is very much in progress. And some areas are still under development, quite a few that we have still needs. Generally speaking though, if we can get good quality data from one of the sources within each column, then we're well on our way in terms of completing the modeling. Next slide, please. Okay, at this point, I will head things back over to Madeline. Thanks.
So we still have a few limitations with the data. As I'm sure you were hearing a little bit from Rick there, all of those red boxes. There's a number of limitations with the data itself. And so these are areas where we know we need data, or where we're still working to identify additional data that we need, particularly from other sectors, both other energy sectors, but then also beyond the energy sector, looking at things like water, agriculture, industry, climate change, so on and so forth. Our next limitation really comes down to access privileges, and these stem from the fact that currently our database is hosted through Compute Canada, and Compute Canada allows access to researchers who have statuses confirmed or sponsored by faculty members at Canadian universities. So currently this is limiting our pool of users to people with some kind of connection to academia. So our future work is going to be migrating this database onto a more broadly accessible hosting platform. And part and parcel with that is going to be a website and a GUI with a nice front end to allow users with different interest or a modeling capacity to be able to interact with the data and connect that front end to the back end, which would retrieve the data, process it, and send it along to the front end. And so taking a step back, just wrapping up here, back to the sort of the beginning of the presentation and coming back to this idea of a national modeling platform. Really, we're hoping that coders can be a foundation that can be extended into a broader series of activities that can really form or contribute to an integrated and national modeling platform that convenes and leverages Canadian modeling capacity to support decision makers in charting and implementing decarbonization pathways. Of course, there's other activities that are part of this national modeling platform. As I mentioned at the beginning, the visualization suite, sort of that second pillar in the broader modeling platform, which is going to come from Mo and Mohammed in the next presentation. And then the repository of open access models, which is really that third pillar. And there we'll be hearing from Robert and Lauren and Maddie about the power, transport, and building systems specifically. So not the entire suite, but a good chunk of the suite. And of course, this is only really sort of the software piece of this modeling platform. Our hope is that this software can then go on to support an ongoing series of modeling forums that really convene modeling teams with decision makers and policymakers in a constructive way to enable a constructive dialogue. So that's all from us for today. I think we've got almost 10 minutes now, for 8 minutes for questions or comments. So we'll open it up at this point.
Yes, thank you, Madeleine and Richard. Yes, we have a bit more than 7.5 minutes if we want to keep our time limit. So anyone want to ask a question? Please go. I think there's one in the chat box. Yeah, so a question on Compute Canada. As a Compute Canada user, how can I get access to the data set?
So we'll be following up on that. At this point, we're still working through making sure we actually have to go through a legal process with the University of Victoria as well. All of our data has come from, well, all of our data on this database have come from publicly available sources, but we do still have to work our way through the legal process before we will be sharing this data broadly, publicly. So the best thing to do there is to take down my email on the screen and follow up with me directly. And then, but we'll be doing a broader announcement once we've sort of worked our way through the legal process, as well as the access around computing.
Thank you. And could you said something about like having all the database is populated with publicly available data, but did you run into some issues getting some data that should be made available publicly and that are not? And what role should the government play, and namely Statistics Canada, in getting more of those data? If there was one data set that you feel that should be made more easily available, which one would it be?
Yeah, that's a great question. And so I'm going to actually, Rick, I'm going to pass it over to Rick's got some of the best, well, all of the best stories about the challenges of actually collecting the data. So Rick, let's pass that one over to you.
Sure. Maybe I'll answer the second question first. What would be, in my opinion, I really think a good set of data around transmission, including substations, both spatial data and operational data, would be very helpful. And it's not as though that data is secret, it's that it's not published en masse. And so just to give you one example, I'm not going to be specific about which utility, but one of the utilities I would ask and say, hey, can I obtain this data? And sometimes it was data that I actually already had. So it's not that I was trying to set them up, it's that I might have had 80 to 90% of a data set. And they say, and the response would be, well, we don't make that public. So that's been really one of the big challenges, is that, in fact, the data is public. It's just that it's not assembled in a way that's usable. And that's what's really been the big challenge here in terms of time and effort. So, yeah, and transmission and substations has been one of the big ones. And hourly data, a lot of inconsistencies. So hourly data is published by 7 of the provinces consistently. Not the same. Like, some make it available almost immediately, like with the ISO and the ASO, it's available the next day, I think. BC Hydro makes it available. Other provinces make it available. Even Hydro-Quebec makes it available. They don't make it easy to find, but it's there. But 3 of the provinces don't make it available. So that's a challenge as well, the inconsistency. So.
Thank you. Some asked if you were in touch with the NRCan and CER for the real-time electricity data project.
Mm-hmm. Yeah, absolutely. Yeah, we had a nice, that was a great EMI presentation a few weeks ago, but yeah, absolutely. So that data is more focused on, as Rick was just saying, sort of more the real-time data, what's actually going on on the system at every moment in time. The database that we're collecting, and then the CER database, we've had a fair amount of back and forth with the Energy Futures team, and they post really good data on both the reference scenario as well as broader energy system data. So, including things like natural gas availability, resources, things like that. And so this data set is a little bit more focused on the power system infrastructure. Where are their generation assets? Where are their transmission lines? What is the load? What is the nodal load? Historically, so more looking at the energy infrastructure. In our actual report, in our EMI report, we didn't really include it so much in this presentation just for the sake of time, but in the report itself, we have a review of the major, by no means not all of the data in Canada, because I think, what data means to an economist, for example, is actually totally different than what we mean by data. But data sort of from our perspective, and we go through sort of the CER reference data and the NRCan, different data sets, the StatsCan data, things like that. So there's a pretty good review there of how where this specific coders database sort of fits within that broader landscape of other databases that are available from different institutions.
Great, thank you. One broad question here: how do you propose to integrate natural gas and petroleum productions sector into this model? In other words, would this model be a whole energy system model?
Actually, we'll hear a little bit about more holistic energy systems model from Mohammed in a few minutes. The message integrated assessment modeling platform that he's been putting together for Canada. So that's sort of, if we're going back to the assessment modeling suites side, that's sort of to the right-hand side of that chart, looking at broader integrated, broader spatial and temporal scale and more energy systems within that. So we'll hear a little bit more from Mohammed on that. This, again, the coders database at this point has been more focused on those more sector specific models. So the power system, the transport system, the building system. And so a little bit more of that granular data and more with more spatial and temporal resolution and more of a sort of infrastructure lens on it.
Thank you. Well, that brings us at the end of our 30-minute period. I do thank you very much for making it in time and keeping it short. Thank you very much.
Thanks, Louis.
Okay, so the second presentation, like Madeleine said, is also from University of Victoria, Mr. Mohammed Miri, that will be presenting. So the control is now yours.
Yeah, thank you, Luis. Thank you so much. So hi, everyone. We actually pre-recorded our presentation. So Preet here, as our colleague, will share the pre-recorded presentation with you, and we will be here for questions. And actually, all of our team are here now, and we'll be here for your presentations. You can start the presentation now, Preet. Thank you. Preet, we are not hearing the audio from the presentation. Hi, my name is Mohammed Niri, and I'm a PhD candidate at CECIT Group, University of Victoria. I'm excited to present our EMI project on an open access integrated platform for visualizing Canadians' transition to a low carbon energy system with my colleague Preet today. The agenda for the presentation will be as follows. We'll first deliver a background and research objectives. Then we'll review the models and methods used in this project. After that, we'll review the results and showcases out of the developed platform. Finally, we discuss the outcomes, future works, and limitations at this stage. Based on Canada's commitment to the Paris Agreement, numerous studies developed modeling tools to investigate the policies and to bring insights for the energy system's transition toward a decarbonized future. These modeling exercises produce diverse outputs which need visualizations to bring better understanding for the non-expert, such as policy analysts, stakeholders, and other communities. Visualizations in terms of plots and charts are effective tools to communicate models' results in an accessible way, which can then foster meaningful insights and effective decision-making. The visualizations options vary from model-specific or generic plot scripts, proprietary visualization formats, and sometimes visualization dashboards. In this slide, we review two visualization platforms developed for two types of energy models. Scenario Explorer is a visualization platform developed specifically for the integrated assessment models, hosted by International Institution for Applied System Analysis, or IASA. Having a common visualization platform was a superb achievement for the integrated assessment modeling community. The Scenario Explorer compares IPCC emission scenarios for established integrated assessment models. Users can upload their model results or use existing results from established models to visualize the outputs and compare results and scenarios. In the electricity system modeling community, visualization platforms are mostly software specific. There are limited options for presenting visualizations from different models in a single space. The options for comparing between models are thus limited. Commercial modeling tools has their own interface and visualization module, but they are rigid and tied to their own base model. Even in the open source models, the visualizations relies on the custom implementations of open source plotting functions. Magma and Kaleidoscope are developed as an open source package by National Renewable Energy Laboratory to plot Plexus, their electricity operational and planning models outputs. They do not accept generic inputs and are bound to receive Plexus specific outputs. In conclusion, most of the visualization platforms only involves the integrated assessment models. Most of them are model specific. Therefore, sectoral and high resolution models are not still communicated in the most efficient way to the stakeholders. Based on the reviewed limitations, and accurately studying the needs from the modeling and policymaking communities, this research is looking for following objectives by developing an integrated modeling platform that includes 5 different model types: integrated assessment models, capacity expansion models, electricity operational models, transportation models, and building energy simulation models. First, this research develops a process flow to convert the results of the models into a standard data format. Second, this study develops a set of plotting functions that use the standardized results to create figures with interactive widgets that allow for quick multi-platform comparisons. Third, the platform developed in this project is accommodating a standardized but flexible format for reporting model outputs. And finally, the project publishes the code in an open, accessible, and transparent manner, completed with appropriate documentation. Adopting different types of energy system models onto a standard data template is a key characteristic in this project. The standard data format is chosen based on the model type, and the data then is post-processed and categorized into different variable types and scenarios. The software-specific details are mentioned in section 3.2 of the report. The platform uses a data template from IAMC for the integrated assessment and capacity expansion models. The IAMC data template originally developed for the integrated assessment models. The data template include model name, scenario, region, and variable names in a time series format. We also developed the second template as part of this project. Results from electricity operational model, transport, and building models. You can see an example of the post-processed output from electricity operational model. You can see generated electricity in an hourly basis for different generation types. This template also works for the transportation and building models. The hourly demand by region or type can be replaced in the same template. The workflow of the platform is as follows. Results from an energy system model is post-processed into a standard data template that is chosen out of the two templates we mentioned previously, based on the model type. The post-process output data template then can be categorized according to user-specified criteria. Followed by the data structuring, plotting function is performed on resulting data structures and then hosted on the visualization dashboard. The plotting functions have the capability to plot interactive plots for the model results. These results are then integrated on the visualization dashboard. The models that are integrated in the platform are categorized based on their data template. First category uses the IAMC data templates that includes two models category. First is the integrated assessment modeling category. These modeling tools help researchers and policymakers understand the long-term consequences of varying socioeconomic development and climate change scenarios across various scales, energy vectors, and sectors. They are mostly used for assessing the costs and benefits related to climate change impacts and mitigation strategies. MessageIS Canada is built from the MessageIS Globium framework, specifically for this project by Sycicity. The model combines different modeling frameworks to assess multidisciplinary policy decisions. Results from these models can answer ambitious global warming goals at least possible cost. Second category is the capacity expansion model, also called as the electricity planning models, and they are electricity system long-term planning models that investigate the least possible cost options for the given scenario and policy choices. These models are designed to address and assess impacts of policies and their relevant scenarios in the electricity system. There are several models developed and implemented in the Canadian domain. The model that is chose for case study in this project is Copper and developed by the CESI team at the University of Victoria as well. The second category belongs to the models that use similar time series data template here in an hourly resolution for the project. The first category is the electricity system operational model that simulate an electricity system's operation over a relatively short period by involving technical ramping requirements and network constraint. They can answer questions about a given generation's fleet's adequacy and reliability in presence of intermittent variable renewable energy resources and with retirement of pollution-intensive plants, thus have a significant role in exploring different policy choices. Several models are developed within the Canadian domain, and this project uses the case of Silver, the model that is developed by CESI team again. The next group and category is the transportation models. Transportation models are designed with the goal of simulating the transportation demand load in various energy sectors. Electrification of the transportation system is targeted and crucial in carbon mitigation policies, specifically in Canada, which 23 megatons of reduction should be contributed by the sector by 2030. The model is that used for this project is the CESI team's transportation model based on TASHA. The next category and the final category is the building models that are designed to simulate energy demands in buildings based on residence comfort, weather data, and buildings' physical specifications. Energy efficiency improvement and demand response potentials are two main factors that makes building a pivotal sector in assessing certain policy instruments. Building sector also contributes a lot in the Canadian national policy goals. The model that is used in this study is also developed by the CESI team and called CESI's Building Modeling Framework. Our whole platform is developed in Python programming language due to its usability amongst various research communities in the energy systems modeling. We use panel library in Python to integrate our visualization tools on dashboard. Panel is an open source Python library that allows users to create custom interactive web apps and dashboards by connecting widgets, such as drop-down boxes, sliders, and buttons to the plots. The decision to use Panel was based on what it provides: a stable platform for hosting apps for the models described. Panel hosts its own tutorial showcasing common operations most developers would want on their applications, that's making the learning curve simple. Also, ease of user interactivity is a priority for this application. Panel also delivers seamless integration of widely used plotting libraries, such as Matplotlib and Bouquet that is used for this project. Here we provide a video tour of the visualization platform. The whole visualization platform is accessible via a GitLab repository.
Hello, my name is Preet, and today I will be guiding you through the visualization platform created by the CESA team at the University of Victoria. Here's the first component of the platform that shows the interactive results from the Message IX Canada Integrated Assessment Model. The drop-down box allows for the selection of various variables such as primary energy, costs, emissions reported from the model. More drop-down boxes can be added given further availability of modeling results, such as navigating between scenarios, filtering out regional results, as well as scenario comparison plots. The second component of the platform shows interactive results from the Copper model. The drop-down box allows us to navigate through the modeling results of various variables, 5 different carbon tax scenarios, as well as regional results from each province in Canada, as well as a total overview of Canada itself. Here are some of the various plots you will be seeing if you decide to play around with the functions. The third component of the toolkit shows interactive results from the Silver model. These interactive plots allow more user-friendly options such as zooming into specific parts of the plot or even being able to pan the graph around to get the exact angle that you would like. Furthermore, zooming into specific parts of the plots and visualizing the aggregated time series data, you can see that the time on the bottom here adjusts, and you can kind of filter the graph to see specific portions of time that you would like to see covered. The drop-down option to choose between different parameters of results are exactly the same as seen before. There are 2 different scenarios in this case. Another important feature is the legend up here. This legend is interactive. If you would wish to remove some pieces of data that you do not wish to see, simply click on its name in the legend and it will disappear. Click on them again and they will reappear. Another relevant tool in the Silver model is the use of the box zoom. On this left-hand section here, there is a small magnifying glass with the label box zoom. If you click that, it will enable for you to be able to pan and cover a specific portion of time to your liking and get a zoomed in version of the data. The reason why this is so useful is the data does not get morphed. It kind of spans to fit the whole graph in front of you. If you would like to zoom in some more, you can do that as well. Simply draw another box and you will have some more data to look at, as well as updated time values at the bottom. The transport model works in a very similar way to Silver. The interactive legend exists here again. The time series data exists as well. Simply zoom in. As well, there is one variable box here, designed to take different months of data. The buildings model works in the same way that Silver and Transport does. Once again, you may highlight and unhighlight different pieces of data depending on what you wish to see, what you don't wish to see. There is a scenario option to load different pieces of data. And in the case of this one, you may zoom as well. And that would also load the time series data and updates the legend accordingly. Thank you for following this guide on the visualization platform created by the CESA team at the University of Victoria.
Here we provide the whole visualization platform is accessible via a GitLab repository. All the packages used in the platform have open source and open access licenses. Moreover, it uses open source Python libraries that are well documented and include tutorials to allow reusability and transparency. The project report will also be available at the EMI website and provides detailed software documentation, model details, and the methodologies adopted for building this platform. There is also a user manual available for this project that explains how new users can easily access, download, install, and apply the fully functional apps for different models. In conclusion, the platform's transparency is maintained based on the documentation, implemented open access codes, and also open source packages included. We invite the contributors and modelers to use the platform and integrate their modeling results on the platform. At this stage, the platform requires a beginner level of Python knowledge to be able to use and implement. At the moment, the platform only integrates sample results from selected models described previously. Also, the plot types are limited for now, although more plot types can be integrated. The user can't directly upload the results and visualize their use cases, and the user might need to adopt model data onto their standard data templates. But in future, we plan to focus on making the platform flexible in terms of model types, the data formats, and also an option that can allow a user to upload their CSV files in a specific format to be able to visualize the results. The key priority is to also host the platform on a web page along with the detailed documentation. The project contributes to the decarbonization pathways of the energy systems for Canada, considering the following factors. The models used for developing the visualization project are state-of-the-art models that contribute to decarbonization pathways individually. However, having these models on a single platform enhances the ability to assess many energy transition scenarios with little effort and in shorter times, allowing decision makers to filter out consistent and practical pathways towards electrification and decarbonization. This helps local and national level policymakers and stakeholders to access regional and national energy transition pathways across timescales, regions, scenarios, and sector-specific models. The results from the various energy system models allows a comparison, enabling a fair assessment of their ability to simulate different Canadian systems pathways. It can potentially motivate other researchers and modeling communities to follow standard guidelines for reporting their modeling results for compelling model comparison studies. The model comparison studies can help the stakeholders better analyze the sensitivity of different scenarios and modeling frameworks. The platform's accessibility features enable a researcher or policy analyst to explore different scenarios of modeling platforms. Finally, the platform also allows modelers to better map the solution space for the decarbonization pathways, which in turn gives policymakers a better idea of how flexible the system is and how to prioritize efforts to transition the pathway in the system. Okay, thank you so much, all. So we're here if you have any questions from us.
Yeah, we still have 7 minutes for questions. Thank you, Mohammed, for that nice presentation. Any questions so far? I would start with one question. What would be the next step in terms of integrating some results in order to better inform policymakers? What do you feel is still missing to make them understand what all those ease the understanding of those results?
Okay.
Mohammed, I hand this question over to you.
Okay, sure. Okay, so as Mo mentioned in the presentation, so this was kind of a beginner effort towards the pathway, and also Madeline mentioned in the previous presentation that we want to build a whole visualization platform. So the results currently which are available on our platform is basically using cases or examples from different model results. So in the near future, we would want to actually host it on a web page, which is live every time, and also we will be integrating some of the more model results from the same models. And in the next steps, maybe in a longer run, we can also plan to integrate more models. So actually, the idea is also we target standardized data formats, right? So if a modeler comes to us and say, oh, I have my post-processed data in a certain data format, so then we will be able to right away integrate that modeling results within our platform. So this is how sort of it works right now.
Thank you. Any other questions? So this is already available, right? Through GitHub, we can access it and try to play with it a bit. Right?
Yes, but as we say, so a user needs to have a basic knowledge of Python right now. So we will be also making sure in the future that so you know if somebody is not a programmer or he is not aware of any programming language, so that user is also be able to play around with the visualization results. So for now, this needs some basic Python skills, which allows you to download the repository and then run the Jupyter notebooks to be able to visualize.
Thanks. There's one question here about the fact is when you're deselecting one variable, are you just simply hiding it, or are you restacking the remaining displayed variable, or is it just a matter of?
Actually, right now the plots do not restack the data that is remained when we deselect. But yeah, I agree that I mean that would be more interesting if the data will be restacked if we deselect the I mean when we deselect the data that we don't need. But yes, you're right.
Okay, so they see it, they saw it right. Okay. Well, and deselecting it, and even probably reordering some of those parameters so to better see.
Mm-hmm.
Yeah. Okay, thank you. So, any more questions, please? Well, in that case, I will thank you all again. And if you could just post maybe post the URL to the GitHub, so if people in the chat, so if people want to access it. Before we post everything online. Thank you.
Sure.
All right. Thank you very much again.
Thank you.
So that will lead us to our third presentation of the day, which would be by Mr. Robert Su from University of Victoria. So, the floor is yours.
Yep. Great. Can everyone see?
Yes.
Okay, perfect. Okay, good afternoon, everyone. My name is Robert. I'm joined today by my fellow group members, Maddie Seidel and Lauren Stanislaw. We are all research students in Madeline McPherson's CSIT group at the University of Victoria, and we are excited to present our research with you today. The topic we will be presenting on is integrated electricity supply and demand modeling to investigate renewable pathways at the city scale. Quick overview of our presentation today. We'll be talking about some of the motivation behind our work, as well as the architecture of the model we've developed for modeling at the city scale. We also propose a workflow between decision makers at the city scale and modelers to help the process between the two parties. And finally, we finish off with future applications and some limitations of our work. So beginning with motivation, our work is focused at the city scale, and part of the motivation for that choice is that a large number of Canadian municipalities have committed to reducing their greenhouse gas emissions. This 458 number is the number of Canadian cities that participate in the Partners for Climate Protection program. And if we think at emissions at the city scale, a majority of those can be attributed to two sectors, the transportation and the building sectors, and we focus on those two sectors in our modeling work. So when we talk about decarbonization, one strategy that comes up and what we're focused on is electrification. And depending on the city, there can be different strategies for electrification. So in terms of Canadian context, there's a lot of room for electrification on the demand side. If you think of technologies like electric vehicles, electric building heating, there's a lot of room for these technologies to grow their market share and become more widely adopted. But in terms of electricity supply, there's some very big differences between regions. For example, Vancouver draws from one of the cleanest electricity grids in Canada, whereas cities like Calgary and Regina may draw from more carbon-intensive grids. So for electrification to be a valid path for deep decarbonization, the electricity that powers these electrified technologies should ideally be low emitting. So for cities that currently have more carbon intensive electricity supply, one strategy for them, along with electrifying their demand sectors, is to integrate more renewable energy into the electricity supply. And this includes technologies such as wind and solar energy. And these technologies are inherently variable. They can't ramp up and down depending on the supply characteristics. And as a result, to avoid undesirable outcomes by integrating these technologies such as curtailment, which is essentially wasted energy, and there needs to be some source of flexibility on the system to accommodate when either the renewable generation is high or if it's low. So this figure shows how both electricity supply and electricity demand can contribute to adding flexibility onto the system. So on the supply side, flexibility can come from energy storage, such as battery storage or pumped hydro, which stores energy if there's a lot of energy being generated that would otherwise go unused. And on the demand side, through a mechanism known as demand response, demand can provide flexibility as well. So demand response basically defined as a shifting of demand in order to match characteristics of electricity generation. And we investigate demand response in the transportation sector through electric vehicle charging, and in the building sector through changing of building heating set points. And the last bit in our motivation section is just to highlight our contribution to what we feel are some modeling gaps that currently exist in the modeling space. So I'm just going to describe some modeling gaps as well as how we try to address it with our city-scaled integrated modeling platform. The first one that has been touched on previously by Professor McPherson was that in some cases spatial and temporal resolution may be too low for some modeling needs in existing city-scale energy models. And we address this using operational models of both the transportation sector and the building sector, so the demand side, as well as an operational model of the electricity system model. And this gives us high spatial and temporal resolution to model variability in renewable energy as well as different spatial characteristics. Related to the first point, demand response strategies, which are a crucial focus of our work as they represent the flexibility of the system and the ability of demand to help integrate more renewable energy. We find that representation of demand response in current models lacks details and accuracy. And using our operational models of the demand sectors, this gives us a greater representation of some of the constraints that demand response faces in terms of preserving consumer comfort, and allows us to represent a wider variety of sectors. Finally, this has been touched on as well. We find that there's a communication gap between decision makers at the city scale and energy modelers, and we're going to present on this as well. We propose a workflow to help translate the knowledge from policymakers upon of which strategies may be more successful into modeling scenarios to help facilitate workflow between the two parties. So I'm going to pass it on to Lauren now, and she's going to discuss in detail our model formulation.
Thanks, Robert. So as Robert mentioned, our platform links together 3 submodels of different sectors, which are the transportation sector, the building sector, and the electricity system sector. And the way that our model works is it runs through 3 different stages. So in the first step, we define a policy scenario, which might consist of adding electric vehicles or switching to electric-powered building heating. I noticed in the chat that someone had asked a question about ground source heat pumps being efficient. And in fact, one scenario that we could add is using ground source heat pumps in buildings, just as an example. And so after defining our scenario, then we pass those new parameters to the transportation and building model, and we model the demand that would be occurring from those sectors as a result of the policy scenario. And then we pass that to the electricity system model. And if you go to the next. And so then, given that information, we can also look at what the electricity system will have to do to meet that demand. And we can understand how much curtailment is being associated with that. So if a lot of renewable energy is being wasted, then we don't want that. That's bad. And so then if it turns out that there's a lot of curtailment, then we run the model again in stage B, where we apply demand response strategies to the transportation and building models. And I'll talk about those a little bit more in the next sections. But basically, we adjust the shape of the demand curves coming from the transportation and building models. Then we run the model again. And then finally, if there's still a little bit too much curtailment after that, then we run the model a 3rd time in stage C, where we add storage technologies. And overall, what this model linkage process does is it enables us to explore different policy scenarios and different pathways by which we can switch to powering our entire city scale energy use by renewable energies as opposed to other non-renewable technologies. If you go to the next slide. Oh yeah, and then finally, if everything works out, then the curtailment rate is found to be acceptable, meaning that, which kind of indicates that we've switched to using renewably generated electricity instead of other electricity sources such as coal. And so that's overall the contribution of our model. If you go next, please. So in the transportation model, this model starts out by defining the transportation infrastructure in terms of the roads that exist and essentially just how different places are connected to each other through means of transportation. And then it takes this information and it can calculate the travel times that it would take to go from one location to another location. And we also look at the characteristics of the population and the trips that they would go on in terms of where they would want to go and when they would want to go there. And given all this information, we then use a model called Tasha to come up with a travel schedule, which basically predicts for the entire city, where are people going and when are they going? And this information is important because when combined with charging parameters for electric vehicles, we can input that information into a charging model and we can understand when electric vehicles are going to need to charge in order for those trips to be able to be completed by electric vehicles. And this gives us the total demand for the transportation sector in terms of the electricity that's being used by electric vehicles to make all those trips. And then finally, if we want to implement demand response, this is done by changing the electric vehicle charging parameters. What I mean by this is normally without demand response, there would be some sort of strategy such as when people get home from whatever trip they're on, their electric vehicle would immediately be plugged in and would charge. But when demand response is applied, since we know when trips are expected to occur, as long as the electric vehicles charge before the trip occurs, then that's fine. But this can be used to time when charging occurs so that the charging can occur when there's curtailment. And this will allow the charging to be powered by renewable electricity, which is good. Similarly, in the building model, it starts out by defining some archetypes, which are representative buildings that are meant to represent the entire building stock in the city. And once we've defined those archetypes, that means that we're assuming what their physical properties are and the properties of the heating, ventilation, and air conditioning equipment, which keep the building at a reasonable temperature and suitable for people to live in the building or do their activities there. And the building model also looks at historical weather and at the temperature set points that people might be using to keep their building at a reasonable temperature. And this information all gets put into a building thermodynamics simulator called Energy Plus, which simulates heat exchange between the building and the environment and is used to calculate the thermal load of the building. And this information is combined with some historical data on appliance demand, which tells us the time when people are using certain appliances, such as turning on their lights or charging their electronics or using home or work appliances. And the thermal demand and the appliance demand are combined to get the individual electricity demand for any building that's being modeled. And finally, since we started this out by modeling only certain buildings in detail, we then multiply by the number of those buildings in the population to aggregate up to the level of the building sector to get the electricity demand for the building sector. And similar to the transportation model, demand response is applied by changing some of the parameters. In this case, it's done by changing the temperature set points. So for example, instead of heating a building to whatever temperature is defined according to industry standards, we might make the building a little bit warmer when there's curtailment on the grid. And this will have the effect of preheating the building so that when the curtailment has stopped being on the grid, the building will be a little bit warmer and it won't need to use as much energy in those first couple of hours or minutes to keep itself at a reasonable temperature. And so through this way, some energy is saved and more renewable energy is used as opposed to other sources. If you go to next slide, please. And finally, the electricity system model is the silver model that was mentioned previously. And this model is linked to the building and transportation models by incorporating their load curve that comes from each of those models, and also incorporating some other load from the rest of the city to understand what the load is. And that tells us the electricity demand for the entire city. And combining this with electricity system characteristics and also with historical weather characteristics, which are used to understand how much renewable energy can be produced from wind and solar, we are able to come up with the user-defined scenario that will tell us basically how much electricity demand there is, as well as how much variable renewable energy is available to power that demand. And then this information is all passed to Silver, which predicts the generation schedule of when different generation assets will need to be running in order to meet the defined demand. And knowing the generation schedule allows us to know the cost of generating this electricity, the associated emissions, and also the curtailment that is resulting as a result of that schedule. And finally, demand response doesn't actually affect the Silver model directly, but it does get passed to the building and transportation models, which change their input. And then that information is propagated through the electricity system model to come up with the finalized costs and emissions and curtailment that are associated with demand response. And so those are the details of all our models. And now I'm going to pass the presentation on to Maddie, who is going to be talking about our overarching model workflow that can be used to facilitate communication between modelers and decision makers.
Yeah, so as mentioned, our workflow that we've proposed is mainly for defining our scenarios. So to really leverage the knowledge of decision makers and policymakers in coming up with these scenarios. So it starts out as any good workflow does with communication between the modeler and the decision maker. Then we've created a scenario template as well as a large list of data sources that we use, which can be passed on to the decision maker to either be filled out or to referred to in the process. And then other assumptions need to be made by the modelers to go to the finalized scenario definition. After that, we run it through the city scale integrated model platform, and we analyze the results. So if you go to the next slide, we're going to go through a quick example of how this would be done. So for this example, let's say that there is a tax incentive being introduced or potentially being introduced for residential buildings to offset the cost of insulation retrofits and electrification. So the decision makers have some knowledge, maybe through surveys or other sources, that they believe that insulation retrofits will be more popular than electric water or space heating electrification. The purpose of the scenario that they want to find out is what will the effect be on greenhouse gas emissions and the cost of electricity. So the first step they would do is to fill out the scenario template with their assumed parameters for the scenario, as well as pass along any relevant data. So the scenario template we've compiled is like a fillable form for the decision makers. The relevant section that they would fill out in this example would be based on the residential building parameters. So this would be an example of how they could fill it out based on the assumptions that they have made on their end. So they assume potentially maybe 75% of viable buildings will electrify their water heaters, and then as well 50% will electrify their space heating, but there's a split between forced air furnaces and ground source heat pumps. And then as well, as the assumption that insulation would be more popular retrofit, they assume that in this scenario that all of the viable houses will. There's also potentially here a note saying that these penetration values are just based off of the percentage of houses built before 1990. The next step is then to pass along any relevant data that the decision makers would like to, or if not, to review the data sources that would be being used by the modelers. So then we would also distribute a table such as this, which would be a data source table, which would list the data source, the purpose of the data source, as well as our preferred data source. If there was relevant data that they would like to pass along, then the decision makers can do so now, or it would be taken from our preferred data source that was listed. So in this case, building type and vintage data sources, we've listed that Statistics Canada census data would be our preferred source. So the decision maker could then decide if that is acceptable for them or if they would like to collect their own data. Potentially an example would be that it's found either from the decision maker or the modeler that 50% of residential building stock is built before 1990 in our example city. And then as well, other assumptions that would be made mostly on the modeling side, but could be run by decision makers as well, is the type of new technology that's being installed, the type of insulation levels, and as well, potentially depending on the scenario, current insulation levels and technologies might be also assumed for comparison purposes. After this, the next step is then finalizing the scenario definition, run through the city scale integrated platform, and then finally analyze results. So skipping ahead to analyzing results, this would be a table of all the possible results that could be found from the city scale integrated model platform, which would be distributed to decision makers. In this case, as can be circled, greenhouse gas emissions and the levelized cost of electricity is the most important one on the decision maker side, as that's what they said they were interested in. However, there are also a lot of other results that may be more important from potentially a modeling or operational side, such as building electricity demand profile, generation asset dispatch schedule, and curtailment. So this would be an example of the model workflow, and I'm going to pass it back to Robert to finish us off.
Sure, thanks, Maddie. So just want to finish off by talking about some applications of our work towards electrification and decarbonization via electrification. So our model is, it doesn't predict technology shares as opposed to some existing models, but it's more suited to taking predictions of certain technologies, the percentage of adoption, as well as what parameters those technologies have to analyze scenarios around that type of information. So I just listed some examples of policies that we can analyze using our model. So EV market share goals, such as Canada's goal of 100% EV market share by 2040. We can also analyze the adoption of building codes, for example, BC Energy Step Code, which specifies energy efficiency targets for buildings. We can also model technology improvements in the different sectors, such as electric vehicle efficiency and improvements in building HVAC properties and appliance technologies. Finally, we can do sort of pathway analysis of meeting renewable energy targets, such as Regina's 100% renewable energy target. And what we've done in one of our case studies was take different scenarios of the generation mix, what percent of solar, how much wind, and evaluate those different scenarios based on the cost to meet Regina's 100% renewable energy target. Some next steps for us. There's lots of work to do as always. A big goal for us will be to add additional features within our sector-specific models. And in the transportation model, this would include adding additional strategies for electric vehicle charging to improve the representation of people charging differently. We want to add different building electrification technologies to improve diversity of what we're able to model, and potentially look into additional strategies to implement demand response as well. We also hope to apply our modeling platform to different cities across Canada. As I mentioned, we have done a case study of Regina, but we hope to apply it to different cities so we can tailor recommendations for different cities to meet their targets, since different cities will have different transportation systems, different electricity systems, and different mix of building archetypes. Finally, we just want to conclude with some limitations. Although we've made an effort to use freely available and open source software as much as possible, there are some places where this wasn't possible. And for example, some of our data collection efforts in the transportation model rely on either licensed software or software that charges on a per price basis. We also have some limitations within our sector-specific models. For example, our transportation model currently does not include a traffic assignment step, which is a crucial part of municipal scale transportation models that are used to evaluate transportation-specific policies. In the building model, our archetype-based approach currently underrepresents the diversity that's actually seen in the building stock, as we're taking just a few sample archetypes and using those to represent an entire city. And finally, we have a relatively simplified formulation of demand response. And in this formulation, shifting of load can create new periods of curtailment within our model, which are not currently considered. But we do hope to address all these limitations if time allows. And that concludes our presentation. Thanks for paying attention, and we're happy to take any questions at this point. Thank you.
Well, thank you all. Great presentation. We still have almost 7 minutes for questions. There is one question here about, well, some question about the scenario design. Are you manually designing those scenarios? And if so, what are the logics for scenario development? And one question that could be linked to that is, well, for example, why are you dispatching the R before adding storage?
Sure, I can take a first pass at this question, and then Maddie, if you have anything to add, feel free. So the way we design our scenarios is a good question. So for our Regina case study, we took some parameters from public opinion surveys. We have a collaborator at the University of Regina who put out a survey asking Regina residents what their acceptance level was of rooftop solar, if they wanted a wind plant outside of city limits. So in terms of generation mix, we were able to take some modeling parameters from that public opinion survey. In the demand sectors, building and transportation, I think in the building sector, we based some assumptions around building standards that are coming up, such as the Energy Step Code. And in the transportation model, we had limited data, so we just assumed 50% penetration of electric vehicles or 100% electrification. Yeah, I don't know. Maddie and Lauren, do you have anything to add?
Adding on to that, yeah, our scenario definition workflow that would be the communication between the decision makers and the modelers is ideally how would we would be like creating these scenario definitions going forward. But again, where data is limited or where we need to make assumptions, we're mainly exploring boundary cases as well as then a few potential intermediate steps because the focus of our application so far have been on somewhat extreme scenarios such as 100% renewable electricity. And then dispatching DR before storage. We believed that the way we had perceived it was with high electrification. We really wanted to explore the impact of demand response in these very high electrification cases, such as with a 100% electric vehicle fleet, as well as all of the building stock having electrified space heating and water heating. So we wanted to really explore the impacts of that, as we thought with all those retrofits, it would probably be more inexpensive to, or less expensive to implement DR before implementing large scale storage. So that was our reasoning.
Oh, thank you. And talking about the building efficiency, how did you create the archetypal buildings for Regina? Did you use already existing data?
Yeah, so I can answer that one because I was the main developer of the building model. So to create the archetypes, first we tried to create archetypes that are representative of the existing buildings as they are. And to do that, for the case of Regina, I used some census data. And from the census data, I was able to determine approximately the year when buildings are constructed, as well as what type of building they were, such as the residential buildings. They could be an apartment, they could be a freestanding house, they could be kind of a townhouse. And then I also could get from the census like the square footage of those houses. And so from those, that was sufficient to kind of estimate the heat capacity or the heat transfer parameters of the materials used, as well as the size of the building, which is an important parameter. And then for actually coming up with envelope modifications, which might be one scenario that we want to explore, those parameters I would get from a building code such as the BC step code, which has different levels of like energy efficiency that you might want to apply to a building. And to speak more generally, it kind of depends on like what data you have available. The census data is pretty good. And also if you had even more detailed data, such as, I know there's a program by Natural Resources Canada where they go around and they do audits of existing buildings to see how energy efficient they are. We didn't use this data because we didn't have access to it, but if someone did have access to this data, that could also be a place where you could get some information about what existing houses look like and how to set up your archetypes.
Great, thank you. So 1 more minute for questions. Anyone want to go for the last one? All good. Well, thank you again. Thank you very much for that nice presentation. That will lead us to the last presentation of the day.
Sorry, yes.
Oh. Yes, what to do? You do want to add something?
Oh, no, I was just, didn't know how to stop the share, but I think you stopped it for me.
Yep. Okay, so that brings us to the last presentation of the day by Yushu Zhao. Yushu, there.
Thanks, Louis. Let me share the screen.
All right, that's all good.
Okay, hello everyone. I'm very delighted to be presenting our research today. I'm Yushu Zhao, a recent graduate student from York University, now a research associate of Professor Christina Hoika. The co-authors for this project are Dr. Christina Hoika, Maria Louise McMaster, and Dr. Runa Das. They are all here today. I'm here to present modeling demand-side low-carbon innovations and their potential to impact on socio-technic energy systems. This research has been funded by Energy Modeling Initiative, internal funds from the Faculty of Environmental and Urban Change, a Social Science and Humanities Research Council Insight Development Grant, and the Smart Prosperity Institute. Numerous studies show that a demand-side transition to electricity plays an important role in deep emission reductions. Decarbonized electrification on the demand side can be achieved through the diffusion of demand-side electrification-related innovations. The extent to which this transformation can be implemented is limited to the disruptive characteristics of the innovation and the diffusion rate of this innovation. There are research gaps in understanding how quickly multiple demand-side low-carbon innovations can be diffused in an urgent and accelerated timeframe. Diffusion of innovation research tends to focus on a single technology or case study, or on a small scope of influencing factors. Our research is critical for filling this gap by creating a novel methodology for identifying multiple demand-side innovations and building a more comprehensive understanding of the diffusion of multiple innovations. Our research investigates how and to what extent do demand-side low-carbon innovations contribute to decarbonized electrification, specifically to investigate the factors that affect the diffusion of demand-side low-carbon innovations and factors that affect the disruptive impact of innovations on decarbonized electrification. In order to explore this research question, we developed two models. Both use Kendall's-Talby correlation to measure the relationships between factors that influence the diffusion of innovations and relations between drivers and inhibitors of scale-up and disruptive characteristics of innovations. In order to identify the innovations, we employed the Energy Technology Innovation System, ETIS. The ETIS approach focuses on how actors, networks, and institutions influence the emergence of novel innovations, from research, development, and demonstration stages to the diffusion stage, providing the knowledge and support for socio-technical energy innovation. Therefore, we use the ETIS as a framework to identify low-carbon innovations. 131 low-carbon innovations were identified in the demand side. Within the ETIS, a policy domain can be used to identify a regime boundary within which governments and institutions deploy policies. To encourage innovation, governments and institutions deploy policy mixes. We identified 4 policy domains across the ETIS to survey, and using desk research and 2 surveys. The first survey is for a range of stakeholders across the ETIS that we identified through public documents and a chain link. And another survey is for innovation providers using a chain link survey and networks. In total, we identified 131 innovations. We constructed those types of variables in our research: dissemination rate, characteristic variables, drivers and inhibitors of scale-up. The coding and conceptualization of these variables create the foundation for the development of quantitative models to empirically assess and quantify the rate of low-carbon innovation diffusion, as well as understanding the broader relationship between the diffusion of innovations and the decarbonized electrification. In order to focus on decarbonized electrification, we developed an electrification framework to identify the innovations that address electrification issues in our datasets. There are 6 types of electrification-related innovations in our dataset. The first is using renewable energy sources, such as the large renewable procurement, a competitive process for procuring large renewable energy projects. The second one is increasing the capacity of electricity storage. The main issue with intermittent renewable energy, such as wind or solar, is the lack of dependable capacity they can offer. Electricity storage technologies can store excess energy and release them when wind speed falls or sunshine is limited. The third one is transportation electrification. such as rechargeable plug-in hybrid and electric vehicles. The fourth is improving the performance of the electricity grid, such as smart grid technology. The fifth is reducing electricity use and carbon emissions with energy conservation, energy efficiency, and demand-side management. For example, building envelope retrofits. However, innovations that reinforcing the existing fossil fuel regime, like fossil fuel furnace, were not included because they are past dependent and work to stabilize the incumbent fossil fuel instead of leading to decarbonized electrification. The last one is fuel switching from a non-electricity carrier to electricity. For example, replacing a natural gas furnace with a heat pump. Within this electrification framework, 114 innovations that address electrification were identified out of 131 demand-side low-carbon innovations in our dataset. The dissemination rate variable was used to assess the state of market diffusion for each innovation. The formula to calculate the dissemination rate is shown at the top of the screen. The population size of the reference market is the number of the potential users of this innovation, which is determined through the desk research. The uptake of the innovation refers to the number of the innovations that are currently in use or purchased by energy users. The characteristics of disruption were captured in three variables: decarbonization, decentralization, and democratization. Decarbonization measures the degree to which an innovation removes carbon from the energy system and supports the adoption of renewable or low-carbon technologies as an indicator of the innovation's potential to disrupt the fossil fuel regime. Decentralization measures the degree to which the innovation geographically decentralized from current centralized energy regime. Democratization measures the degree to which the incumbent gains control, or whether citizens or communities gain control of the energy system. So the policies that drive or inhibit the scale-up of niche innovation play an important role in influencing socio-technical regime change through the diffusion of disruptive demand-side low-carbon innovations. Three policy variables were constructed to analyze the factors that influence the disruptive characteristics of the electrification-related innovations and the diffusion of the innovation. Policy for scale-up economic instruments. Economic instruments measures the degree to which economic instruments are used to drive or inhibit the scale-up of an innovation. Economic instruments are economic incentives or market-based schemes that provide energy users with motivations to adopt innovations. The second one is policy for scale-up regulations. Regulations measures the degree to which regulatory instruments are used to drive or inhibit the scale-up of an innovation. Regulatory instruments are direct regulations that aimed at controlling the actions of energy users through command and control. The last one for policy variables is policy for scale-up knowledge creation and diffusion, which measures the degree to which knowledge creation and diffusion instruments are used to drive or inhibit the scale-up of an innovation. Policy instruments can be general or technology-specific policy instruments. General policy instruments aimed at providing general support or regulations to an entire industry without pinpointing any particular technology, such as carbon tax and cap and trade. Technology-specific instruments support specific innovations. Regime change is unlikely to occur without technology-specific policies to support niche innovation. If the policy instrument is general, this policy was coded as having incremental impacts on the scale-up of the innovation. If the policy instrument is technology-specific, this policy instrument was coded as having disruptive impacts on the scale-up of the innovation. The last is the legitimacy variables. Building legitimacy for niche innovations to support their scale-up is also a key factor that influences socio-technical system disruption. Based in the literature view, two legitimacy support variables were developed. The first is legitimacy through discourse framing, which measures the degree to which discourse drives or inhibits the scale-up of an innovation, which is building legitimacy of niche innovations through positive discourse framing or visioning strategies by actors. The second one is legitimacy through actors and networks, which measures the degree to which actors and networks drive or inhibit the scale-up of an innovation. The presence or absence of actors, such as individuals, organizations, and institutions with agency, will influence the diffusion of niche innovations across multiple scales. So that's all of the variable construction. Three characteristics of disruption were analyzed by developing a coding scale to measure the extent to which the innovation was regime reinforcing, neutral, incremental, or disruptive, as shown in this table. Although the scale for each variable was developed independently, this table describes a general coding scale and explanation of each score, from -2 to +2, as they relate to measuring disruption. The key findings are that the correlation between dissemination rate and economic instruments variable is highly statistically significant and of medium strength. The correlation between dissemination rate and decarbonization is statistically significant and of weak strength. Statistically significant effects of other variables on dissemination rate cannot be found. So the modeling results indicate that demand-side low-carbon innovations with the potential to lead to decarbonized electrification pathways are associated with lower rate of diffusion. In addition, electrification-related innovations with technology-specific policy support through economic instruments are associated with higher rates of diffusion compared to innovations with general economic policy instruments. Another finding is that the correlations between characteristics variables and the drivers or inhibitors of scale-up, the correlation between decarbonization and economic instruments is statistically significant and of medium strength. This negative correlation indicates that innovations with more disruptive decarbonization potential usually receive less technology-specific economic support compared to innovations that have incremental impacts on the socio-technic regime change. The correlation between decentralization and each legitimacy variable is highly statistically significant and of medium strength. The correlation between democratization and economic instruments is highly statistically significant and of medium strength. The correlations between democratization and each legitimacy variable are statistically significant and of medium strength. No statistically significant correlation can be found for any other characteristics and support variables. So the last one we can see from this table, correlation between two legitimacy variables is highly statistically significant and of strong strength. The correlation is also positive between these variables. So we can conclude from our modeling results that first, innovations with the potential to lead to decarbonized electrification are actually associated with lower rates of diffusion. The second is innovation with technology-specific economic policy support are associated with higher rates of diffusion. The third is innovations with the potential to lead to decarbonized electrification are associated with less technology-specific economic support. Therefore, more technology-specific economic policy instruments are needed to accelerate diffusion of demand-side electrification-related innovations. We can also conclude that innovations with the potential to lead to decentralization and democratization are associated with more legitimacy support. Legitimacy through actors tend to be a precondition to legitimacy through discourse framing. Therefore, legitimacy support is an important driving or inhibiting force for innovations to lead to decentralization and democratization. A strong network of system actors should be established to increase the legitimacy support. The models developed in our research have the ability to assist policymakers in mapping the existing range and combination of policy and legitimacy supports that drive or inhibit system-wide decarbonization within their jurisdictions. Correlation analysis between the individual variables and the dissemination rate can be used to examine how to drive or inhibit diffusion of an innovation within a particular context. To determine whether across a mix of innovations in a particular energy system, system reinforcing innovations are receiving more policy and legitimacy support than innovations that support decarbonization and electrification pathways. For example, providing more support for the scale-up of efficient natural gas furnace compared to deep retrofits of building envelopes coupled with heat pumps. So to support decision-making about how to provide optimal policy and legitimacy support to the right mix of low-carbon innovations to diffuse into markets and support decarbonization and electrification pathways. For example, whether disruptive innovations can decarbonize, decentralize, and democratize the energy system, or whether complementary innovations such as solar and wind power or electric vehicles are receiving similar support for scale up to achieve optimal outcomes. The details of the model are provided in our master's paper recently published in an open access journal, the Master's X Journal. The theoretical framework, the sampling design, the data gathering, codebook design, coding process, and inter-rater reliability test, correlation analysis, and results interpretation for the model are all outlined in this master's paper. So also software used in our research, including Cortex, Excel, Google Docs, and SPSS statistics are all accessible online. Alternatives to this software are also easy to access online. So I may say our models are very transparent and accessible. While this research focuses on the context of Ontario, the analytical framework and the lessons learned from these research models can be applied to other contexts. Since electricity systems are governed and managed by province and territories, practitioners or policymakers have to apply these models to each province and territory individually. In the context of Canada, energy systems are controlled and under the authority of provincial governments, and as such, the factors that facilitate the diffusion of low-carbon innovation in the province of Ontario may differ from those of other Canadian provinces. To integrate the research models in a national modeling framework, we can have workshops with practitioners or policymakers from all provinces and guide them through how to do sampling design, data gathering, data coding, correlation analysis. So one of the benefits of integrating the research models in a national modeling framework is to increase data accessibility. The major limitation of the models was access to sufficient innovation uptake and population data. Being integrated in a national modeling platform presents opportunities for future collaboration in filling those data gaps. The integration can also contribute to the improvements and the expansion of the research models. So that's all. Thank you.
Well, thank you very much. Great presentation. Great. A lot of interesting information there, at least to me. Are there any questions already? Or I would maybe go with one question if no one wants to add to or ask a question right now. you said about the actors. Did you also consider and maybe this is outside of the research, and tell me if it is, but have you also considered the availability of skilled workforce for integrating some of the innovation, or would that fall outside of the scope of that project?
Actually, we do not include this in our research, but yeah, that's definitely an interesting question. The availability of the workforce will definitely influence the innovations. They will influence the innovation adoption, and also especially will influence the behavior of the end energy users, I guess. So yeah.
Well, at least this information would be of interest, so that if we put forward some programs and make sure that we also train, we have the proper amount of people to work on integrating those technologies, right?
Yes, definitely.
Any questions? Please feel free to either unmute yourself and ask it directly.
If I can just add to that, the model would take into account the workforce through the knowledge creation and diffusion, and also through the actors. But all of the variables were based in the sustainability transitions literature. So that's how we picked each one for that particular innovation.
Okay, thanks. Anyone with questions?
Yeah, hello. Just have a question. So those concepts like democratization and decentralization, I'm just curious how you would try and evaluate those for, I don't know, a technology like electric vehicles. Like I'm just very curious how that would go about.
Just as I mentioned, the decarbonization measures the degree to which an innovation removes carbon from the electricity, the energy system, and supports the adoption of renewable no carbon technologies as an indicator of the innovation's potential to disrupt the fossil fuel regimes. So at the electric vehicles, as you mentioned, we will code it as a positive too, because it has very disruptive impact on the fossil fuel regime. And also for the decentralization, which measures the degree to which the innovation geographically decentralized from current centralized energy regime. So we may say electric vehicles will have impact on the decentralization, because it will drives the innovation geographically decentralized from the current centralized energy regime. And for the last one, democratization, which measures the degree to which the incumbent gains control, or whether citizens or communities get control of the energy system. So for this one, if the example is electric vehicles, we will not see it has much impact on the democratization. I hope that answers your question.
Yeah, definitely. I was curious because, like, on one hand, maybe like in coal and natural gas dominated power grids, that's electric vehicles not necessarily contribute to decarbonization, or yeah, I guess there's sort of trade-offs that you probably consider as well. Interesting, thank you.
Yeah, thank you for your question.
We do have time for some more questions. If no one comes with a question, I would have another one. Could you said something about the fact that there was correlation with more correlation with the technology, innovative technologies, more than with GHG reductions, or something like that, right?
Yeah.
So that was linked with the the type of measures that were put in place that you saw, or how do you make the difference between the two, or how did you see that there was a difference between the two, and what could explain the difference?
Are you talking about the technology specific policy instruments, or the
that's the technology specific instrument, or technology specific versus emission reduction?
Yeah, so in our research, we kind of divide all the policy instruments into two categories. One is like general instruments, another is technology specific policy instruments. So those general policy instruments aimed at providing general support or regulations to an entire industry without pinpointing any particular technology. For example, the carbon tax or the cap and trade scheme, all of them are just try to remove the carbon from the energy system, but not pinpointing any particular technology. But technology-specific instruments support specific innovations. So we're thinking that regime change is unlikely to occur without technology-specific policies to support this niche innovation. So if the policy instrument is general, this policy will code it as having incremental impacts on the scale up of the innovation, which is +1. But if the policy instruments is technology specific, this policy instruments was coded as having disruptive impacts on the scale up of the innovation, and then we will code it as +2. I hope that answered your question.
Yes, thank you. But I would see that there is a not necessarily a risk there, but instead of pushing technologies, it would be better if we just set objectives and let the various actors there come with some possible innovations. But I guess this is not what the data is showing right now, right?
Yeah, definitely. Yeah. And
could we link that with the fact that most programs are designed with evaluation performance criteria for civil servants that do implement them based on those numbers of system installed? Instead, it's easier to achieve numerical targets like how many systems that we deployed instead of targets on GHG reductions, right? So that could be the way we do evaluate those programs and how people get evaluated on the efficiency of those programs, right? So if I take in Quebec, for example, the example of electric vehicles, right? We set a number of vehicles without linking it specifically to a GHG reduction target. So I guess civil servants don't want to be associated with a failure, let's say, right?
Yeah, I totally agree. Yeah.
Yeah, but it's interesting to see that the data shows that yes, we do tend to favor those technology-specific programs. Thank you.
Thank you.
So we have 1 minute more, maybe, or one last question. Well, if you don't have any more questions,
if I could just interject too. What our data shows is that, like the literature says, technology-specific is stronger, is what you should put together. But what our data finds is that there's stronger economic policy instruments for technologies that are fossil fuel, that are heavily reinforcing the fossil fuel regime, rather than having economic instruments for technologies that decarbonize the fossil fuel regime. That was one of our strongest findings.
Yeah, and that's an interesting one to remember, right? Or to do. Yep. All right, we're at the end of our 2 hours session. I will thank you all for attending and specifically thank all of the presenters. I do thank you, especially because you did respect the time. Thank you very much. And I will remind you that there are some more presentations that will be held during the next 2 weeks. So the next one will be in 2 days. And if you want to look at the complete schedule, please go at the website address that is there, and there is still time to register to the next 4 sessions. With that, I will thank you all, and please stay safe and see you soon. Thank you very much.